Hi everyone, today a video in the Transition Metals and Inorganic Reactions series, looking at an introduction to transition metals, complex ion formation and isomerism. So the elements of titanium through to copper lie within the D-block elements. Remember that we define our periodic table in terms of the S block, groups 1 and 2, the P block, groups 3 through to 8, and the D block as being that chunk of metals in the middle. And so the elements from titanium through to copper lie within the D block elements. And these are metals, and so they have they're good conductors of heat and electricity. They're strong, they're shiny, they're hard, and they have high melting and boiling points because they have strong metallic bonding. That delocalized sea of electrons and the positively charged ions, there's good electrostatic attraction between. And we know that as we go across a period, we add electrons into a D sub-level. So if we're talking about these D elements here from titanium through to copper, we're adding them into the 3D sub-level. So it's easiest to think about filling up these electron configurations if we actually start from the start of our fourth period of the periodic table. So that's starting at potassium. So if we think about our electronic configuration for potassium, we're going to fill this using the Aufbau principle. And this really is a combination of Hund's rule and the Pauli exclusion principle. So Hund's rule says that electrons fill orbitals singly before they pair up. So if we're filling up the p orbitals, each one of those 3 p orbitals has 1 electron in before they start to pair up with 2. And the Pauli exclusion principle states that electrons can only occupy the same orbital if they have opposite spins. And so by this, when we draw our electrons out, we normally draw them as these kind of half arrows. And so what we really mean is that we have an arrow going up and an arrow going down. We can never have 2 arrows going up or 2 going down. We have to have 1 up, 1 down. And so our Aufbau principle really is that we fill our orbitals according to those 2 rules. We also fill the lowest energy orbitals first. And so typically our 1 are below the 2 are below the 3. And so the diagram I've shown here kind of in the middle on the right is a useful way for remembering the ordering of the energy, these subshells. So we fill our 1s orbital first, then our 2s, then the 2p, then the 3s, then the 3p. Now, what you would expect is for the 3d orbital to be next. However, actually, it is the 4s orbital that is slightly lower down in energy than the 3d. So the 4s fills first, and then the 3d. Now, the reason for this is twofold, really. The principal energy levels, that's the number, the 1, the 2, the 3, or the 4, actually get slightly closer together as you go further and further from the nucleus. So the gap between the first and second is slightly bigger than the gap between the second and third, is slightly bigger between the gap between the third and the fourth. And so we have our energies getting slightly closer together. Combine that with the fact that we're splitting these quantum shells, these levels, into sub-energy levels, into the different orbitals, the p, the s, the d orbitals. It actually means that the 4s orbital is of a slightly lower energy than the 3d orbitals, and so it gets filled first. Another way to think of it as well, another energy consideration, is that actually as you go across, so as you go from an s orbital to a p orbital to a d orbital to an f orbital within the same period, these orbitals become more contracted, smaller. And so a d orbital, a 3d orbital, actually is smaller than a 4s orbital. And so therefore filling a 4s orbital is a bit more favourable because the electrons have a bit more space in there. They've got more room to get further away from each other. Imagine filling our orbital with 2 electrons, the electrons are going to repel. They want to get as far away from each other as they can do, and they can do that more in a 4s orbital than they can in the 3d. And so if we think about potassium, we start to fill up our electron configuration. It would be 1s2, 2s2, 2p6, 3s2, 3p6, and then remember the 4s fills first, so 4s, we've got 1 electron in our outer shell. If we then go across, the next element across is calcium. Here we're just going to continue filling this up. We have to fill up the 4s, we have to have our Pauli exclusion principle going on here, so we have an arrow going up and an arrow going down for opposite spins. And so we now pair it up into our 4s orbital, and it becomes 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. And now we reach the D-block elements. So the D-block elements are, of course, scandium through to zinc for this fourth period. And so if we look at scandium, we're now going to start to fill a D orbital. The reason they're the d block is because our outer electrons, if you like, are in the d orbital. The reason that calcium and potassium are the s block is because the outer electrons are in an s orbital. The reason, for example, why aluminium and phosphorus are p block elements is because their outer electrons are in the p orbitals. So we've had our 4s filled. We've said our 4s is lower energy than the 3d. So we've filled our 4s. So the next orbital that we start to fill up is now the 3d orbitals. And there are 5d orbitals. Remember that there's 1 s orbital, 3 p orbitals, 5d orbitals, and 7 f orbitals. And so we start to fill these, again using Hund's rule here, that we fill them singularly before we pair them up. That's just simply because, again, less electron-electron repulsions if they go into separate orbitals rather than going into the same one. And so generally, we just use these rules that we've been looking at in the past 2 examples to fill up our d electrons. So they go into single orbitals. Once there's 5 of them, they then start to pair up. However, you have to be careful because there are 2 special cases. The first is chromium. So if we're just filling up our electrons as we go along, we have started at scandium and we had 1 electron in our 3d. Going across to chromium, we're going to add some more electrons in, and so you would expect the electron configuration to end in 4s2, 3d4. However, the actual electron configuration for chromium is that it ends in 4s1, 3d5. So one of those s electrons has been promoted to our 3d orbital. Now, how can this happen? The reason it happens is because this promotion to make 4s1, 3d5 is more stable. It's a lower energy arrangement than the arrangement where we have 2 in the s and 4 in the d. Now, the reason for this that we have to know for A-level here is to think about it in terms of electron-electron repulsion. I have 4 electrons in my d orbitals. They're all unpaired. But I have 2 electrons in my s orbital. Now, while my s orbital is still technically bigger than the d orbitals, there's still electron-electron repulsion between those 2 electrons. So what I can do instead is promote one of those electrons to the 3d. Remember, I said the 3d and the 4s orbital energies are fairly close, so it doesn't take so much energy to be able to promote that electron up. And in doing so, I now have 6 orbitals, all that have 1 unpaired electron in. So now all the d orbitals just have 1 electron in, minimised our electron-electron repulsion. And our 4s orbital has gone from having 2 electrons with big electron-electron repulsion to just having 1 electron. And so we've reduced the electron-electron repulsions. Overall, we've made a more stable electron configuration, one of a lower energy. And we always want to get the lowest energy one we can. And so generally, as we're going across, you have to watch out for chromium, because rather than being 4s2, 3d4, it is 4s1, 3d5. Now, another factor, which is a bit beyond A-level, is something called exchange energy. And essentially what this boils down to is having half-full subshells, is being a bit more energetically favoured. Now, you can look into it if you want. It's a bit physicsy, really, but essentially it's also energetically favourable to have these half-filled shells. So not only have we reduced the electron-electron repulsion by having 4s1, 3d5, we've also increased this exchange energy. We've increased the number of half-filled orbitals. The other example to watch out for is copper. Now, as we go across, we had our chromium, 4s1, 3d5. The next one along, manganese, reverts back to the normal filling. So it fills the lowest energy orbital possible. That's the s orbital. So our manganese would be 4s2, 3d5. And then we carry on going. We then start to fill up our d electrons again. We now have to start pairing up our electrons. And so, for example, iron would be 4s2, 3d6. And we go on and on and on, and we reach copper. Now, again, we would expect, if we're just filling it normally, for it to be 4s2, 3d9. And hopefully, maybe again, you can see that you could achieve a more stable configuration by promoting one of those s electrons again up to the d orbital. And so we now get electron configuration that ends in 4s1, 3d10. So it's exactly the same idea as we had for the chromium earlier on. This idea that we have our electron-electron repulsions in our 4s orbital, 2 electrons that are paired up. Actually, we can achieve a more stable configuration by promoting one of those electrons up to the 3d orbital. So pairing it up in the 3d orbital actually is a bit more energetically favourable than pairing it up in the 4s. Now, while you might think that the 3d orbital, again being smaller, has more electron-electron repulsion, there's also this idea again of the exchange energy, and this exchange energy says that essentially if we have half-filled shells or completely full shells, these are more energetically stable. And so actually, even though we've increased the electron repulsions by putting an orbital into the other d orbital, pairing all of those up, because we now have our 10 electrons in our d orbitals completely full, plus a half-filled s orbital, we actually have much more exchange energy. And so it's always this sort of balance between energy. We also have our 4s orbital being lower down in energy, and so therefore it's again a bit more energetically favourable to not have the electron repulsion in the 4s orbital, but to have it in the 3d orbital. And so again, the two to watch out for are copper and chromium, because these have either a half-filled or a full d orbital and a half-filled s4s orbital. So always remember that chromium and copper are the two to watch out for. So here I've drawn the full electron configurations for starting at potassium and working our way through the S block, potassium and calcium, and then through the D block elements from scandium through to zinc. And so you can see that generally we apply our Aufbau principle, we fill our lowest energy orbitals first, we fill them singularly before we pair them up. And you can see that typically we said that our 4s orbital was just slightly lower down in energy than the 3d, and so hence the 4s fills before the 3d does. And that really there's only two examples we need to really have in our head here as kind of exceptions to the rule, which is chromium and copper. And this is where we promote one of our 4s electrons up to the 3d. It's a very small energy difference, so we can promote one of these electrons up to the 3d subshell. And this creates, in the case of the chromium, a half-filled S and a half-filled D subshell. And in the case of the copper, a half-filled S and a full D shell. Now in the case of the chromium, we said that was to minimize electron-electron repulsions within the 4s orbital. It also increased our exchange energy, having more half-filled orbitals. And in the case of the copper, we actually slightly increased the electron-electron repulsion by putting our electron from the S into the D orbitals, but we massively increase our exchange energy. And so those are the reasons that we end up with these slightly more, stable low energy arrangements that are shown in red. Now when electrons are removed, when we ionize these, so for example ionizing these metals, they actually come from the 4s orbitals first. So if we take the electron configuration for our vanadium, 3d3 4s2, it's actually the s electrons that are lost first. And so we lose the 2 from the s if we're making the 2+ ion to make 3d3. Likewise for chromium, remember we have that slightly odd configuration, 3d5 4s1. To make chromium 2+, I lose my 4s electron first, and then I lose one of the d electrons to make 3d4. If it was chromium 3+, I then continue taking away the d electrons, so I end up with 3d3. Now this might seem slightly counterintuitive, how we can fill the 4s orbitals first when we're doing our Aufbau principle and filling them, yet when we ionize them, we lose it from the 4s first, even though we've said the 4s is of a slightly lower energy than the 3d. Now, there's a couple of reasons why this kind of is a bit wrong, essentially. The electron configurations that we've written above here are for neutral atoms in the gas state. So the minute that we put these elements into contact with other atoms or other molecules to actually make compounds, the 3d level tends to drop below the 4s level. So when we take these atoms and we actually put them into compounds and these become solids and in solutions and stuff like that, actually our 3d level tends to drop below the 4s in energy. Therefore our 4s is the highest in energy and gets lost first if we take electrons away. Also, if we just think about the atoms themselves in the gas state, the ordering of these orbitals is quite challenging, and the actual real reason for why this kind of breaks down in terms of 4s is filled first but lost first is way beyond A-level standard and quite complicated. But essentially we have this big energy balance going on. We have the actual energy of where the orbital is in terms of how high or low energy they are. You have your electron-electron repulsions, you have your exchange energy. There's so many different factors to consider in terms of how what the actual electron ordering is in our atom. And so typically when we fill our atoms up, we follow that Aufbau principle. Lowest energy orbitals first, and so the 4s is of slightly lower energy than the 3d because as we go from shell to shell, they become slightly closer together. We split it into our s and p and d and f subshells, and And so we end up having, plus also the 3D being slightly smaller than the 4s's in terms of the size of the orbital, we end up having our 4s being slightly lower energy than the 3D. The problem comes, though, when we actually start to fill these orbitals with electrons, because as we fill them up with electrons, we start to get big differences in the electron-electron repulsions, in the exchange energies, in the attraction between the protons in the nucleus and the electrons in these shells. And it's this big energy balance that actually means typically when you've filled all of your electrons up, while you might have filled it so the 4s fills first with the Aufbau principle, actually when it exists as this atom, due to all the energy balances, the 4s orbital actually becomes slightly higher in energy than the 3D. But as I say, the real reason is really quite complicated. The key takeaway message is that the 4s electrons fill first and the 4s electrons are lost first on ionization. So time to have a go at writing out some electron configurations for these ions here. So have a go, and the answers will be on the next slide. So the first example here is our Fe3+ ion. So the way that I normally go about doing these questions is to write the electron configuration first for the neutral atom that we saw on the previous slide, and then to work out what the actual configuration is for the ion, remembering that we fill our 4s first and we lose our 4s first. So if I was writing out the electron configuration just for an ion atom, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6. So that's using our Aufbau principle there to sort of fill that up. Then we remember that we lose our 4s electrons first, and so sometimes you'll see these electron configurations written with the 4s before the 3d. That's our kind of filling order. Sometimes you see it written with the 4s after the 3d, and that's essentially our sort of true energy ordering, if you like, once we've made our atom. And so we lose the 2 electrons from the 4s first. It's an ion 3+ ion, so we also have to lose 1 from d orbitals as well. And so our electron configuration ends in 3d5. The chromium 3+, remember that chromium was one of our slightly odd ones. We had chromium and copper, being this idea where we promote one of our s electrons to the d orbitals. And so the neutral configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d5. Then it's a 3+ ion, so I lose one of the s electron, I take away 2 from the d, and I'm left with a configuration for this 3+ ion as 3d3. And then finally the zinc 2+, again write out the normal zinc configuration first, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. It's right at the end of our d block, so we've filled all the d orbitals up. And 2+ ion, we lose our s electrons, not the d orbital ones first. The s electrons are lost first, and so we lose our 4s2 electrons, and the arrangement just becomes 3d10. So we actually define a transition metal element, to be an element that forms at least one stable ion with an incomplete d subshell. So what this actually means, as we talked about on the first slide, I said that the d block runs from scandium through to zinc, but our transition metal elements run from titanium through to copper. And this is because scandium and zinc aren't actually defined as being transition metals. This is because scandium only forms the 3+ stable ion. If you work out your electron configuration, take away the 2 4s electrons, take away the 1d electron, that leaves you with a d0 configuration. So technically, I suppose it's incomplete, but actually it needs to have some electrons in to be incomplete. Here we don't have a d subshell at all, technically. Zinc only forms the zinc 2+ stable ion, and as we saw on the previous slide, that zinc 2+ configuration ends in 3d10. So because that's a complete d subshell, because our scandium 3+ is an empty d subshell, neither of these are actually defined as transition metals. It has to have an incomplete d subshell. And so therefore scandium and zinc are DBlock elements, but they are not transition elements. The transition elements are from titanium through to copper for the 3d subshell. And transition metals have 4 main properties that we're going to talk through in these series of videos that are common to all of the transition metal elements. The first is complex ion formation. So transition elements tend to form complex ions. And so these, for example, are the chromium hexaamine complex there, so CrNH3 3+, or this iron hexaaqua complex, FeH2O6 2+. So remember, a complex ion essentially is more than one type of atom that has a charge on it. So just a standard F- fluoride anion is a simple ion. Something like these, where we have lots of different atoms and quite a big structure with an overall charge on it, is a complex ion. The second is colour. So the majority of transition metal ions are coloured. So for example, the Fe2+ ion, if it's aqueous, is green. The copper 2+ aqueous ion is blue. And we'll see in some later videos both why these transition metal ions are often coloured, and also actually we will start to look at the colours of lots of different ions and how the colours can change when we do reactions. And so transition metals tend to be quite pretty to look at because they have nice colours compared to sort of organic molecules and main group elements that tend to normally be colourless or white solids. The next one is catalysis. So many transition metals actually show catalytic activity. So for catalysis, many transition metals show catalytic activity. So remember, a catalyst is something that speeds up the rate of a chemical reaction without being chemically changed, providing an alternative pathway for the reaction to proceed down, one that has a lower activation energy. And so, for example, finely divided iron is used in the Haber process to make ammonia from nitrogen and hydrogen, and V2O5, vanadium oxide, is used in something called the contact process to make sulfuric acid. And we'll see in a later video lots of different processes that use transition metal ions for catalysis. And then finally, variable oxidation states. So transition metals can show more than one oxidation state in their compound. Now this isn't particularly groundbreaking. There's lots of main group elements, lots of elements such as, for example, nitrogen, phosphorus, that tend to show different oxidation states in various different compounds. The key thing with transition metals is that it's so easy to be able to go between different oxidation states. And the reason for this is because our d orbitals are very close in energy. And so it's very easy for these electrons to kind of be redistributed, lost and gained very easily. And so it's very easy, for example, for chromium to show chromium 2+, chromium 3+, for manganese to show Mn2+, Mn7+. So it's very easy for transition metals to show more than one oxidation state in their compounds. So the first one to talk about is this complex ion formation. So all transition metal ions can form these coordinate dative covalent bonds by accepting electron pairs from other ions and molecules. So remember, a coordinate dative covalent bond is where we have, rather than a normal covalent bond with both partners of that sharing one electron, here we have one partner of it being electron deficient, the other being electron rich, and so sharing both of its electrons. So our metal, having our empty d orbitals, is electron poor essentially, and it can accept electron pairs from other ions or molecules and create these dative covalent bonds. Now, an ion or molecule that forms a coordinate bond to a transition metal is something called a ligand. So these could be sort of things that we quite often think as nucleophiles, having lone pairs that can be donated. So things like NH3, H2O, chloride anion, cyanide anion, stuff like that. Anything that has a lone pair that can be used to donate in a coordinate bond to our transition metal ion. We call these ligands. Now, multiple ligands can bond to a single transition metal ion, and this is what creates our complex ion. So at the bottom, you can see that we have this copper complex ion, 6 water molecules, each of them donating one pair of electrons in these coordinate bonds, and we have this complex ion, a 2+ charge spread out over this whole molecule, over this whole ion here. Now, the number of coordinate bonds that the metal has to it is called the coordination number. So the coordination number is simply how many coordinate bonds do we have. Now, the key thing is that this is not always the same as the number of ligands. As we'll see on the next few slides, we can have some ligands that can make more than one coordinate bond. They have more than one lone pair that can be used in the coordinate bond. Now, the examples I've shown at the top here, the ammonia, the water, the chloride anion, and the cyanide anion, even though some of them have more than one pair, those are all examples of what we call monodentate ligands. They only make one coordinate bond. So the key thing is that the coordination number is the number of coordinate bonds. It's not always the same as the number of ligands. And if we dissolve the salt of a transition metal in water, what we actually create is a complex ion. The metal ion becomes surrounded by water molecules, and these water molecules act as ligands. Now, normally, 6 water molecules can fit around a metal ion in an octahedral arrangement, all those bond angles of 90 degrees. And if we have 6 water molecules, we call this species a hexa-aqua ion, literally 6 waters, essentially, hexa-aqua. And so an example would be if I have copper sulfate, copper CuSO4, if I dissolve this up in water, what we actually create is the copper hexa-aqua ion, copper H2O6, the 2+ ion, and then we also have our sulfate anions, the SO4 2- anions floating around as well. And so when we dissolve it in water, we don't just think of it now existing as just copper 2+ and the sulfate 2-, but actually as our copper hexa-aqua ion, the water molecules making 6 coordinate bonds to that copper hexa-aqua ion, and our sulfate anion. Now this coordination number idea, the number of coordinate bonds that we have, links to the shape of the molecule. They're related to each other. Now, if you're not so happy with shapes of molecules, you can go back to my video in the bonding and structure series and look at the video on shapes of molecules. And essentially, the key thing that dictates the shape of our molecule is how many electron pairs are around our central atom. And we said in that video that if we have 6 pairs of electrons, this tends to be an octahedral shape. And so ions that have a coordination number of 6, i.e. 6 coordinate bonds to them, are usually octahedral. Ions with a coordination number of 4 are usually tetrahedral. They can sometimes be square planar. And ions with coordination number 2 are often linear. So there's some examples that are shown here in the middle. So we have this chromium hexaamine complex. So 6 ammonia ligands. Each of these have a lone pair that can be used in a coordinate bond to our chromium. And so we form this complex ion here, this chromium 3+ complex ion. But because we have 6 coordinate bonds, it's an octahedral structure. For our coordination number 4 coordinate bonds, we said it can either be tetrahedral, and most often is tetrahedral. So remember, tetrahedral is our four electron pairs arranged with 109.5 degree angles to minimize these electron-electron repulsions. And so this copper chloride anion here, CuCl4, is an example of a tetrahedral molecule. They can also be square planar. So we'll see later on that this depends on different factors to do with how crowded the molecule is, what we call the sterics of the molecule, how big the ligands are, and also to do sometimes with the electronics of what ligand we have attached. But an example here is this nickel CN4 complex ion, so 4 cyanide ligands. We each have a lone pair that can donate to our nickel. And in this case, we actually have a square planar complex. So this is, here we have our bond angles of 90 degrees. So you can see that the bond angle in a square planar complex is smaller than the bond angle in a tetrahedral complex. And so typically if you have a larger ligand, that's going to want to have a bigger bond angle and get further away. And then finally, something like this diamine silver complex, AgNH3-2, is an example of a linear complex, 2 coordinate bonds, and therefore a linear complex. And you may recognize that as the ion that's present in Tollen's reagent when we think about the distinguishing test between aldehydes and ketones. Now, as I said, there are reasons why some of them are square planar and some of them are tetrahedral for coordination number 4. The 2 reasons are the electronic stabilization, that's literally what our electron configuration is of our metal, and also the size of the ligands. Now, the electronic part is a bit advanced for A level, but really what we can think about is the size preference, and we can predict that quite easily. Chloride ions, if you think about where chlorine is in the periodic table, are actually quite large, and they're larger than the cyanide anions or the water molecules. And so we can think about this being period 3 for the chlorine versus period 2 for the carbon and the oxygen. They're typically going to be bigger atoms. And so therefore, physically, less of the chlorine ligands can fit around the metal. So that's an example why we have this copper chloride species only having 4 chloride anions rather than 6. Physically, only 4 of them can fit around that central metal ion. They're much bigger than the ammonia ligands that we have in the previous example there. But also we can start to predict whether things are likely to be tetrahedral or square planar simply based off the what we call the sterics, how many can fit around that metal. And then if we have a smaller ligand, there might be a preference for it being a square planar molecule because we have smaller bond angles of 90 degrees. Whereas if we have a much bulkier, bigger ligand like the chlorine or the chloride anion, this will probably have a preference for being tetrahedral because there's larger bond angles of 109.5 degrees. Now, the ligands that we've discussed already, the ammonia, the water, the chloride, the cyanide anions, these are what I said are called monodentate or sometimes unidentate ligands. What that means is that they bind to an atom using a lone pair of electrons, one coordinate bond. They just use one of their lone pairs to bind to the metal. But some molecules or ions will have more than one atom that can bind using a lone pair of electrons. So typically, even as I said in the unidentate example, say for example the water, we have two lone pairs, but typically we only use one lone pair from one of those atoms to actually make our coordinate bonds. And so some molecules or ions have more than one atom that can be used to donate our lone pair of electrons in these coordinate bonds. And these are what we call multidentate ligands. Now this dentate that you've been hearing at the end of these words literally comes from denticity. You can think of biting down, dentists and teeth. We're thinking about the ligands kind of biting into our metal. And so the denticity is simply the number of coordinate bonds a single ligand can make. So if it makes one coordinate bond, it's a monodentate ligand. Sometimes we can have two coordinate bonds. So this is called a bidentate ligand. This is where we have two atoms. Both are capable of forming these coordinate bonds. And so we have two examples here. One is called 1,2-diaminoethane. So simply we have our ethane carbon skeleton with two amino groups, two NH2 groups on. Both of those groups have lone pairs, and so therefore both nitrogen atoms can act as ligands in this. This essentially is a multidentate, a bidentate ligand. So we have one molecule able to make two coordinate bonds. And this is where I said that the coordination number is not the same as the number of ligands. We can have an octahedral species with this ligand, but we only require 3 of these ligands because each ligand can make 2 coordinate bonds. And so your coordination number is still 6. There are 6 coordinate bonds, but there's only 3 ligands. So it's why it's important to note that the coordination number is the number of coordinate bonds, not the number of ligands. And this 1,2-diaminoethane quite often is just simplified down to En. Another one on the right here is this ethane dioate. So essentially the sort of dicarboxylic acid it would have been originally that's been deprotonated to form these carboxylate anions on both sides. This is often called the oxalate ion. It's C2O42-. But again here we have 2 oxygen, negatively charged oxygens that have lone pairs that can form these coordinate bonds. And so again we have 2 atoms that are capable in the same ligand and therefore a bidentate ligand. Now there are examples of lots of other types of denticities. So you can have denticities of sometimes ligands being able to make 4 coordinate bonds. There's lots of different examples. But another really important example to know for E-level is something called EDTA. This stands for ethylene diamine tetraacetate. So if you break that name down, ethylene diamine, well that's exactly the same as the 1,2-diaminoethane that we had, essentially almost. And then we have this tetraacetate, so 4 acetate groups. And that's exactly what the structure ends up looking like. We have this ethane bridge in the middle. We have our amino groups on the end, so our nitrogen atoms. And you can see that the hydrogens in the 1,2-diaminoethane have been replaced by these acetate groups, the CH-COO groups on the end. And there's 4 of them. Now this is an example of what we call a hexadentate ligand, hex meaning 6. So this can actually make 6 coordinate bonds for one ligand. Where you can use the 2 nitrogen atoms that are neutral with the lone pairs, and we can use the 4 negatively charged oxygens, the lone pairs from there. So this can make 6 coordinate bonds, a hexadentate ligand. And if we end up making a complex ion with a polydentate ligand, so something greater than a monodentate, it could be a bidentate or it could be this hexadentate ligand here, anything greater than 1 coordinate bond for the ligand, the complex ions are what we call chelates, and we'll see why on the next slide. So these complex ions with ligands that can make more than 1 coordinate bond are called chelates, and this relates to something called the chelate effect. So if I add a hexadentate ligand like the EDTA 4- to a solution of a transition metal salt, the EDTA will displace all 6 water ligands from the hexa-aqua ion. So the example could be that we take our iron, hexa-aqua ion, FeH2O6, 2+ ion. Remember, the water molecules are neutral overall, so they don't affect the charge on that iron atom. I can react it with my EDTA, and the EDTA will simply kick out all 6 water molecules. And so we end up producing FeEDTA. That's now a 2- ion. We have to make sure our charge is always balanced in these equations, make sure the atoms balance and the charges balance. So EDTA is a 4- overall, the ion's 2+, so put them together and you end up with 2-. And we've kicked off every single water molecule, so 6H2O. Now if you look at simply the number of species on either side, we've started off with 2 species and we've ended up with 7. And this causes a huge increase in entropy, a huge increase in the randomness and the disorder of our chemical system. Now, if you're not happy with entropy, go back to my video on the thermodynamics topic, and there's a video to do with entropy. But essentially, the more molecules we have on the right-hand side, and we have more than we do on the left-hand side, we've increased entropy. We've increased the randomness and the disorder of our chemical system. An increase in entropy is massively favourable. And so this is why this reaction is driven towards the products. It's why if you put these two, if you mix EDTA and these hexaacyl ions together, they actually react together. They don't sit there and don't react. They will react together and all of the water will get kicked off. And so chelate complexes, these are these complex ions with multidentate ligands or polydentate ligands, are favoured over complexes with monodentate ligands. And so typically if you have some reactions where you put some ligands in where it can either form monodentate, form bonds with monodentate ligands or form bonds with polydentate ligands, it will always choose the polydentate ligand because of this increase in entropy. If you think about replacing the water molecules with a monodentate ligand, say just natural ammonia rather than EDTA, you'd have 7 on the left and 7 on the right. There'd be no increase in entropy there. However, by using even just a bidentate ligand, you can actually have more molecules on the right-hand side than you can on the left, and so an increase in entropy. And so it's this entropy increase which really drives these chelate reactions. And so the chelate effect is seen in the molecule of hemoglobin. So hemoglobin is the red pigment in blood. It's responsible for why the blood is red in humans. And it's responsible really for transporting oxygen around the body. And so the structure of it is shown there on the right. It consists of an iron 2 plus ion in the centre. And it has a coordination number of 6. We have 6 coordinate bonds. 4 of these sites are taken up by quite a complex ring system that we call a porphyrin. This is what we call a tetradentate ligand, so it makes 4 coordinate bonds. And this is this kind of this ring structure that you see surrounding the iron atom. And so this is the heme part. This is called a heme complex. That's where the name sort of comes from. This is the heme bit of the name. Now the 5th site of it is taken up by a nitrogen atom below the plane of a ring from a protein that's called globin. And so you have this kind of nitrogen atom that's at the end of this protein chain that can bond to the iron atom from below the plane of that porphyrin ring. And that part, the protein part, is actually named globin. And so hence this is why the name is hemoglobin. You have the heme part, which is the ring in the 4 nitrogen atoms in the ring in the centre. And then finally this 5th site being the protein globin, which binds using another nitrogen atom, another nitrogen lone pair, but from below the plane. And so what this leaves is a 6th site that is open. This is an octahedral species. It's a 6th site that we haven't used yet. And so this 6th site can accept an oxygen molecule as a ligand, an O2 molecule as a ligand. There's lone pairs on that oxygen that can act as a ligand. Now what you might have heard of is that carbon monoxide poisoning is very bad. And carbon monoxide poisoning can actually be fatal. And the reason for this is because carbon monoxide competes for this site. And carbon monoxide is actually a better ligand than oxygen. We can think about this simply in terms of electronegativity. We have either we're binding through an oxygen atom or we're binding through a carbon atom. Carbon is far less electronegative than oxygen is, and therefore the lone pair is much more readily donated from the carbon than it is the oxygen. The oxygen prefers to hold on to it a bit stronger because it's more electronegative. And so carbon monoxide is a better ligand than oxygen is. And so if you have carbon monoxide and oxygen present, it will always take the carbon monoxide over the oxygen. And because it's such a good ligand, it binds to the iron atom, the iron ion, and it actually binds irreversibly. So you can't then get it off and put the oxygen back on. It blocks oxygen from being able to be transported around the body. And so this is the origin of the poisonous effect of carbon monoxide, and it's actually the reason why you can actually die in a room with plentiful oxygen if there's carbon monoxide there. Even though there's way more oxygen, it simply can't get onto the hemoglobin molecule because the carbon dioxide has beat it to it, essentially. So the last thing to really talk about is isomerization in transition metal complexes. So we've always talked about isomers before in terms of organic compounds, and we know that we can have structural isomers and stereoisomers. Now remember that structural isomers are compounds that have the same molecular formula, the same overall formula, but they have a different connectivity of atoms. They have a different structural formula. And we can say that these really are position isomers, chain isomers, and functional group isomers when we were thinking about our our organic molecules. And that stereoisomers are compounds that have the same structural formula, so they have the same actual connectivity of atoms, but they have different arrangements of atoms in space. They are arranged in 3D differently. Now, transition metal complexes show stereoisomerism. And remember that the two types of stereoisomerism are geometrical isomers and optical isomers. Now, our geometrical isomers is our cis and trans, or our Z and our E notation. We've seen Z and E before in alkene chemistry. And optical isomers were, when we talked about, we've seen these before, and we've talked about enantiomers, these non-superimposable mirror image forms of our molecule, where we have chiral centers, where we have our asymmetric carbon atoms we talked about in the optical isomerism video, where we have overall chiral molecules, like your hands, non-superimposable mirror images. Now, they show various other forms of isomerism, but the two we need to really know about for A level is geometrical and optical isomerization. So the geometrical is typically seen in octahedral and square planar complexes, and essentially is where we have a mixture of ligands, and we can either position these ligands to be either cis, 90 degrees relative to each other, or trans, 180 degrees relative to each other. And geometrical isomers will have different chemical and physical properties. They're actually different molecules, essentially. They have different chemical and physical properties. And so the example here at the bottom is this chromium complex ion with 4 water ligands and 2 chloride ligands attached. And these chloride ligands could go 180 degrees to each other, essentially top and bottom. That's a trans isomer. But we could have the chlorine atoms going 90 degrees to each other, cis to each other. So there's 2 examples of the cis isomers I've drawn here. One where they go literally directly next to each other. That's a 90 degree angle there between those 2 chlorines, as well as actually a 120 degree angle. If you look at the further, the rightmost example here, we have the 2 chlorine atoms actually are 120 degrees to each other. And so that's also a cis example. So cis is kind of 90 or 120 degrees, kind of close together. Trans, 180 degrees, the furthest they could get apart, essentially. Now, for the other type, the optical isomerism, this is our non-superimposable mirror image forms of each other. And this occurs for transition metal complexes when there are at least 2 bidentate ligands in a complex. Remember, bidentate meant that we had 1 ligand forming 2 coordinate bonds through 2 different atoms. And these optical isomers are chiral. And remember that if you're not so sure about chirality, go back to my video on optical isomerization. But this optical isomerism means that our enantiomers here, essentially our optical isomers, have identical chemical and physical properties. They're only distinguished through their effect on polarized light. They turn polarized light. One enantiomer turns it clockwise, one enantiomer turns it anti-clockwise. That's the only difference between the 2 of them. And so our example down here is this chromium complex ion again. Now you can see here that I've drawn it as 2 nitrogen atoms with this kind of this link between them. Not really a proper actual chemical linkage I've drawn here. This is quite often a way that you can represent. So through this example here with the 2 nitrogens, I might actually be representing that EN ligand, that 1,2-diaminoethane ligand, where we have our 2 NH2 groups, and then we have our 2 carbon atoms that bridge them. Rather than draw that, I mean, that one's a fairly simple one to draw out, but if you have slightly bigger ligands, it's quite often simpler just to draw the 2 atoms that are actually involved in making the coordinate bonds, and then to draw this kind of wiggly line between them to indicate that they're joined together. As long as you state that that's what you're doing and that the line in between them represents the rest of the ligand, it's fine to draw that out because it's simpler. But you can see here that you end up actually forming this molecule here has 3 bidentate ligands in. You can see that in the octahedral complex we have 3 of these bidentate ligands, and we form these non-superimposable mirror images. So remember that when we draw out these enantiomers, we have to make sure we draw our molecules out in the proper 3D orientation using the wedge and the dash bonds. So we draw our octahedral species out, and hopefully you can see that these are non-superimposable mirror images. If I put these 2 things on top of each other, they will not superimpose on top of each other. It's like your hands. They don't superimpose on top of each other. You can also get it in square planar complexes. So here we have a bidentate ligand over on the one side, and then 2 chlorine ligands on the other side. And again, you can see a mirror image line down the middle. If I put these 2 isomers, these 2 optical isomers, the 2 enantiomers on top of each other, these are non-superimposable. They don't lie directly on top of each other, all the atoms matching up. So the two to really be aware of is geometrical, the cis-trans isomerization, and the optical. Now, transition metal complexes are actually often used in medicine, and one of the most common ones and one of the most well-known ones is actually cisplatin. And this is one of the most effective drugs against many forms of cancer, even though despite it was actually synthesized and first made many, many dozens of years ago. So it's quite an old drug, but actually it still works quite effectively. And we're, as the name suggests, with cisplatin, we're looking at the cis isomer of the complex, so that geometrical isomerism. And so here we have a platinum metal with two chloroligands and two amino ligands, essentially, two NH3 groups. Now, these NH3 groups, or the Cl groups, they could go trans to one another, 180 degrees, or they can go cis to each other, 90 degrees. And that's what I've shown right at the bottom of the slide. There's our cisplatin, two NH3 groups that are 90 degrees to each other, two chloro groups that are 90 degrees to each other. And this is a square planar complex. Now, cells divide to make more of the same type of cell. And before cell division occurs, a copy is made of the DNA in the cell. And after cells divide, the two cells are created with exactly the same DNA. It's copied that plan for the DNA. Now, cancer spreads by the division and replication of a cancerous cell. So there's been some kind of genetic change here, which means that we now have a cancerous cell. And what this means is that as we divide and we replicate this cancerous cell, and one of the actual kind of defining properties of cancer is that you have cancer cells dividing and replicating much more quickly, much more rapidly than healthy cells do. Essentially, they bypass all of the mechanisms for repair and for checking the DNA, and they just pass straight through and are allowed to divide and replicate. Now, the way that cisplatin works is it actually binds to DNA. And so it binds to the DNA of the fast-growing and replicating cancer cells. Again, the cancer cells replicate more quickly than healthy ones do. And remember that DNA has that quite ordered double helix structure. And by binding to the DNA, it distorts this double helix structure. Essentially, it makes the double helix bend out of shape. And by making it bend out of shape, the overall effect of that is that the cell can't reproduce. By bending it so much out of shape, it stops the reproduction, it can't get repaired, the repair mechanism is unable to fix this kind of massive kink in the chain. And therefore, with the cisplatin bound, it can't repair the actual DNA, and therefore the cell dies. It goes through something called apoptosis. It's a kind of suicide for a cell, essentially. It's got nothing else to do other than just kill itself. Now, one of the reasons this works is because the cancer cells are dividing much more rapidly than healthy cells are. And so if you put your cisplatin in, it's much more likely to find a cancer cell than it is a healthy cell. So this is one of the reasons why cisplatin works. It actually also affects healthy cells as well, but it affects cancerous cells more because they are rapidly growing and dividing more quickly than healthy cells are. But the key thing is that cisplatin can't tell the difference between cancerous and healthy cells. And so actually it does also attack healthy cells, and so it kills off healthy cells. And so this is the cause of very, very sort of several unpleasant side effects that you get if you ever have chemotherapy. So this is things like hair loss, fatigue, sickness, hair loss in particular because, as we said, the cancer cells are much more rapidly growing and dividing than healthy cells are. But of healthy cells, it's quite often hair cells that are actually the fastest growing themselves. And so they get affected the most as well. Now, there have been several alternatives that have been developed that can be given in lower doses and therefore have less side effects, so you feel better when you're having chemotherapy. One of these is carboplatin, which is the example shown there where I've got the cisplatin on the left, on the right is carboplatin. And so you can see that I've replaced the two chlorine groups with this kind of carbon-based structure. And actually what this is it's essentially a worse leaving group. The way that cisplatin works is by binding to the DNA, it has to kick off the chlorine ligands. Now actually this carboplatin thing, again you can see that carboplatin ligand is actually a chelate. And chelates are more favoured than monodentate. What it means is that it's much harder to kick off. And so therefore it works more slowly, it can be given in lower doses and less side effects. Now if we go back to cisplatin, it's actually only the cis isomer that is active as a drug. the transplatin, where we have the chlorine groups 180 degrees to each other, actually isn't active. And the way that this works is how cisplatin works. So cisplatin goes into the body. The chlorine ligands get lost to start with. So in the body they get lost and they get replaced by water molecules. It is then these water molecules that get replaced by binding to DNA. So when the DNA comes along, essentially you have your nitrogen bases in DNA. It's actually the guanine base of DNA that the cisplatin binds to. And the way it works, as you can see in the middle picture with the cisplatin, is it binds to two adjacent guanine bases. So two of these guanine bases that are next to each other, essentially, in the chains. And it binds to two of them. And the reason that works is because the chlorine groups that have to be lost are 90 degrees away from each other. They're fairly close. And so it's able to do this, what we call an intrastrand link. However, if it's trans and we have them 180 degrees away, there's no physical way that both of those chlorine groups can be lost, and then the H2O groups that are there, they can't actually bind to two adjacent guanine bases. They can bind to one, sure, but they can't bind to two of them that are adjacent. It's really binding to the two that are next to each other that causes this massive sort of distortion and bending of the DNA and the eventual death of that cell. And so therefore, because it can't bind to DNA effectively, only the cis isomer is the one that is active. So, time to have a go at some questions. So if you'd like to have a go at these questions, pause the video, and the answers for these will be on the next slide. So the first question here was to give the definitions for a complex, a ligand, coordinate bond, and a coordination number. So a complex is simply the combination of a transition metal ion and ligands that are bonded together. So we talked about complex ion formation. It doesn't have to be an ion, it can just be a complex. And what it is, though, is a transition metal ion with ligands that are bonded to it. A ligand is a species that can bind to a transition metal ion, bond to it, via a coordinate bond. So it's typically something that has a lone pair that can donate that lone pair via a coordinate bond to bind to our transition metal ion. And the coordinate bond, of course, is this special type of covalent bond where rather than having one electron shared between each atom, we actually have both electrons coming from one atom, both electrons coming from one of the partners. So both of the electrons come from our ligand, in this case our lone pair, and are donated to our metal ion. And then the coordination number is the number of coordinate bonds. So not the number of ligands, the number of coordinate bonds. Question 2 was to give the possible structures for palladium with two NH3 ligands on and two Cl ligands on, sorry. So this is exactly what we've just been talking about. This essentially is a cis or trans platin. And so we can have cisplatin, where the two Cl groups and the two NH3 groups are cis to each other, 90 degrees. Or we can have it where our two NH3 groups or our two Cl groups are trans, 180 degrees to each other. And so this, remember, is a type of stereoisomerism. And it's actually our geometrical isomerism, our EZ isomerism, or our cis-trans isomerism. Question 3 was then to write an equation for this copper hexaaqua ion reacting with excess Cl-, and to draw out the shapes and to say, well, why are the shapes of the product and the reactants different? Now, if you remember, we haven't quite covered actually writing out these equations yet, these ligand substitution reactions where we substitute our waters for the chloride anions. But hopefully you can remember from a few slides back that we said that our copper with 4 chlorine ligands on was this tetrahedral shape, CuCl4. And so we can write our equation here that we have copper, this hexaaqua ion, 6 water molecules, so copper, H2O6, is a 2+ ion, reacting with 4 Cl-. This produces our copper chloride complex ion, CuCl4, the 2- charge on. Remember, everything has to balance in terms of atoms and charge. And then we kick off our 6 water molecules. And so our first hexaaqua ion, our reactant, is an octahedral molecule. It has 6 coordinate bonds, so octahedral. Our copper chloride complex ion has 4 coordinate bonds. And we said this typically can be tetrahedral or square planar. But typically chlorine ends up being quite often tetrahedral because it's quite large as a ligand. And so we go from an octahedral to a tetrahedral shape. And the reason is that Cl- is a much larger ligand than H2O. You can think of it as being in period 3 rather than period 2. and so less can physically fit around that central copper ion. And so I've drawn the structures there at the bottom. There's the octahedral and there's the tetrahedral. Remember, when we draw these structures out, we have to show with the proper 3D arrangements. That's using dashed and wedged bonds as well as normal bonds. And the final one is to draw and state the type of isomerization for this copper complex. So you have copper with 2 En ligands. Remember, the En is this 1,2-diamino ethane, and then 2 water ligands. And so our En, remember, our often called ethylene diamine, or our 1,2-diamino ethane, is a bidentate ligand. It's got 2 atoms, both of which can donate lone pair through a coordinate bond. And so I'm going to draw it here again using this kind of this cheating method, if you like, just showing the 2 nitrogen atoms linked together. And you can see there at the right, I've just said that En equals that 1,2-diamino ethane ligand. And so you can just kind of, as long as you say that's what you're representing with that kind of line between the 2 nitrogens, it's fine. And so we can draw these 2 bidentate ligands next to each other, and then the 2 water ligands in the 2 remaining spaces. And remember that I said if we had octahedral species, so here we have technically 4 ligands, but our coordination number is 6 because we have 6 coordinate bonds. That if we have an octahedral complex with at least 2 bidentate ligands, that we could have our optical isomerization. So remember, that's another form of stereoisomerism. This is where we have our non-superimposable mirror image forms of our molecule. And so here you can see I've drawn the mirror image of it. So you have the one on the left, the one on the right. Just simply imagine a mirror down the middle and imagine the mirror image of it, the opposite of it. And then you can imagine that putting those 2 on top of each other is non-superimposable. And so there are our enantiomers, and this is our optical isomerism. So thank you for watching this video. You can find many more videos like this on my YouTube channel. If you found the video helpful, please consider leaving a review on my tuition website. I offer online tuition for chemistry, so please check my tuition pages for prices and how to contact me. And if you need any more help with your chemistry, you can feel free to drop me an email. I'll be happy to help.